In this presentation, we will understand different data types, examine basic control network architecture, look at basic gateway hardware, use different data types in gateway configurations. Networks and devices need to be connected for data gathering and sharing, but they don't always speak the same language or have the same structure. The raw data we're going to look at is generated by instruments in the field and can exist in many different forms. This then needs to be converted to be understood further along the line. First, let's have a brief look at some data types. Every device in the field will need a signal input to operate, or will generate an output, or will do both. These signals are known as I/O. The main types of data in industry are analog I/O, discrete I/O, and digital data. Analog I/O is usually 4 to 20 milliamps or 1 to 5 volts. This can also be transmitted as a digital signal, such as in a VFD, where the analog signal is transmitted as a series of small digital steps. It is usually associated with any output that varies, such as temperature, pressure, flow, etc. Discrete I/O are simple on-off signals which can be transmitted by either voltages or digital signals. Voltages can be sent as bits, such as digital ones and zeros. These are usually alarms, counters, relays, etc. Digital data is binary ones and zeros and has the ability to transmit lots of data very quickly. This data is used in larger networks where large amounts of data are being quickly transmitted. Some devices that transmit digital signal data are barcode readers or RFID readers. Any of these data types will need at least a TCP/IP header if they want to travel on a routable network. This is any network which uses routers or switches to transmit data, such as an Ethernet LAN. Modbus TCP has an advantage in that it is a flexible client-server network, but the timing will be inconsistent. I/O messages are set at dedicated speeds and will have priority over routable client-server data. This makes them more suitable to high-speed, repeatable communication at device level. DeviceNet is an example of I/O communication which can be configured to a set speed and polling arrangement. Just to make things more interesting, each of these data types could also be referred to as serial communications. When we talk of serial communications, all this means is that this type of data is being transmitted using a serial protocol or topology. This could be a serial protocol such as Modbus RTU or CAN, or topology such as the RS485 or DeviceNet. Client-server networks tend to be the higher level networks where large quantities of digital data are exchanged. These are not usually time-critical operations, such as accessing an Excel database or sending an email. Device-level networks tend to use I/O data or messages in a master-slave configuration. These networks send smaller amounts of data, but in a reliable, consistent, time-critical manner. It is possible for a controller, such as a PLC, to act as a client, a server, and an I/O master within a network. The I/O messages will have priority over client-server data as they are set as time-critical, whereas the client-server data will be sent and received as the processing power becomes available. All these data types are transmitted according to a set of rules, known as protocols, over a suitable network. Where two networks meet, these different types of data can be exchanged to another network and protocol using a gateway. It's the configuration of this gateway which will determine how reliable the connection is between the field devices, the controller, and the higher level network. A gateway can be any device which allows devices on different networks to communicate with each other. They repackage and convert data going from one network to another so that information can be understood. This is known as interfacing and allows networks with different architectures and protocols to communicate. SCADA hosts and HMIs are usually in a higher level network, so are generally configured as clients. Field level devices, such as drives or sensors, are generally configured as server or I/O message slave. Gateways act as a single point of access for monitoring an area of operations and can communicate with a wide variety of devices and controllers. The gateway may act as just a simple protocol conversion using impedance matching devices, fault isolators, or signal translators to pass information back and forth between different networks. It may also be a more sophisticated device with an operating system and applications capable of storing and filtering sensor data in a network, then passing it on to a data center or to the cloud. There are universal gateways which will be capable of handling many different protocols which are specific to a particular industry, and there are gateways that are only for converting between specific protocols. The type of configuration you will need for your gateway will mainly depend on what devices you are using, what speed you need the data to be running at, what protocols you are using, and whether you have access to the PLC program or not. Here is an example of a typical gateway configuration. The PLC communicates using DeviceNet and the HMI communicates using Modbus TCP. Clearly, a gateway will be required to enable the two networks to communicate in the most efficient manner possible. Straight away, the HMI will need to be configured as a client, which means that the HMI side of the gateway will need to be configured as a server. If the PLC side of the gateway is also configured as a server, this means the PLC will act as a client. What this means in practice is that the PLC will need to wait until any other I/O messages are processed until it can deal with the client server data. This may not be a problem if a very fast update speed is not required. Configuring the PLC as a client will also mean that the access will be needed to the PLC program. This is not always possible or desirable for all controllers. On the positive side, as the PLC is a client, it will be able to see the gateway on the network through the PLC software. This can save a lot of time troubleshooting if there is a problem with the gateway. In this example, communications is desired between a standard PLC running DeviceNet and a custom PLC running a proprietary protocol. The custom PLC software is not available for configuration, so the gateway is configured as a client and the custom PLC will act as a server. As the gateway has no ladder code to execute and can be set up with a defined polling rate to the custom PLC, this will provide fast, consistent communications on this side of the network. The standard PLC can then be set up as a client, with the gateway acting as the server, but this means that the PLC's ladder code will need to be executed for communication to occur. This slows down the process. To solve this problem, the gateway could be set up as a client and the standard PLC as a server. This would speed up the communication due to the PLC's code and wouldn't require any program changes, but this would also mean that the gateway would be invisible to the PLC, as it is the client that initiates communication. This means that if there is a problem with the gateway, the PLC or any HMI connected to it will not be able to diagnose the issue, which could lead to some extended downtime. The best solution is to use dedicated I/O messaging. This sets a dedicated update rate between the PLC and the gateway, which gives fast and consistent communications. The PLC program can also use tags to identify gateway problems or other network issues. I/O communications are the fastest and most consistent connections and should be used whenever high speeds are required and if the protocols used support it. In this example, the PLCs are configured as I/O masters and the gateway as an I/O slave. This means that each PLC program will need to be accessed and that full network diagnostics will be possible. In this example, a PLC that runs DeviceNet will need to communicate with a series of drives which run on Modbus TCP. Modbus TCP is a client-server protocol, not an I/O protocol, so the drives will need to be configured as servers and the PLC as a client. Using an Ethernet communications module, the PLC is able to be programmed to accept Modbus TCP packets, which gets the PLC talking to the drives, but with unpredictable timing results, as client-server communications rely on currently available processing capacity. Also, if one drive goes offline, the rest of the drives will need to wait until the offline drive times out before communications can be resumed. This will lead to further unpredictable timing results. Ideally, a gateway can be installed which supports multiple clients so that each drive communicates on its own channel. This allows all clients to communicate without relying on other clients' connections. And these can also be configured as I/O messaging, which ensures high-speed communication but will require access to the PLC program. In this arrangement, if one drive drops out, the communication with all the others is not affected. The way devices and controllers can communicate is determined by the type of data they use. Industrial communication data is generally analog I/O, discrete I/O, or digital data. I/O communication is generally used at the device level and consists of smaller amounts of data being transmitted at a regular defined speed, usually called a master-slave configuration. A client-server network can move large amounts of data but will generally be unpredictable in its timing, as it is capable of using higher-level networks, switches, and protocols. The quality of network possible is determined by the devices which are being used. Some devices can only be configured as a client or a server. What protocols are being used? Not all protocols can support I/O messaging, which means that they will need to be configured as client-server communication. Whether or not you have access to the PLC program. To use I/O communication or set up a gateway as a server, the PLC code will need to be changed.